Well, good morning, everybody. Thanks for joining us on a Friday morning here. Today's talk will be done by Dr. Mark Hanigan of Virginia Tech, balancing lactating dairy cow diets for amino acids now and the future. Some couple of housekeeping points before we get started. We'll take the questions, any questions at the end, so feel free to use the question tab on the side there or the raised hand function. And with that, I'll turn this over to you, Mark. Thanks for being with us.
Well, thank you for having me talk today. This is sort of an unprecedented time in our careers, I guess, and so it's an interesting sort of approach to things. But I'm going to spend a lot more time probably on balancing in the future than balancing now, but certainly we need a perspective of where we've come from in order to decide what the direction is that we need to go in the future. And I should recognize my graduate student, Jacqueline Prestegard, who's contributed to this line of work and some of these slides. So if we look at some of the reasons why we might be interested in this or should be interested in this topic, there's a couple large ones, okay? And the first one maybe is not at the top of your list, but I think longer term it is a big issue, and that is that when we look at the efficiency of nitrogen use in our production species, the cattle end of the spectrum doesn't do quite as well as the simple stomached animals, the pigs and the poultry. And that's important because the dietary nitrogen that's fed, which is contained in the protein that we're feeding, if it's not captured in growth tissues or fetus or milk, then it's excreted. And that excreted nitrogen, of course, can have value if we can apply it to the soil and get crops to use it for plant growth. But unfortunately, more than half of the nitrogen that we excrete in the manure, or that is excreted in the manure, is lost as ammonia. And so it's converted to ammonia in the slurry or in the pile, and that ammonia, of course, is a gas, and so it volatilizes off and goes up into the air. And it contributes when there's ammonia in the air, along with some nitrogen or sulfur oxides, which are coming from burning, fossil fuels in cars and power plants and so forth. It forms these really small particles in the air that causes the haze that you often see in higher population density areas. And that haze is a problem because it's becoming fairly clear that that's one of the contributing factors for the increased incidence of asthma in humans. So anytime we start doing things that impact human health, of course, we're probably not going to win those arguments long term. The other problem is that once it gets into the air, of course, it floats all over, and when it rains, then it'll be washed out of the air and be deposited in areas where we may not want it, and in particular, environmentally sensitive areas. And of course, I'm speaking from very near, a fairly large one, which is I'm sitting in one that we may not talk as much about, because actually Blacksburg, Virginia, believe it or not, is in the Mississippi watershed. The new river that flows through this area down into North Carolina actually drains into the Ohio, and so we're sitting in the Mississippi watershed. But just over the mountain, just literally a few miles away, it's in the Chesapeake Bay watershed. So that watershed's had a lot of effort put into it in terms of trying to reduce the water quality problems. So once we lose it in the air, there's all sorts of damage that can occur. And of course, we aren't capturing any of the value out of that. So it's essentially neutral at best and negative at worst. Of course, the bigger reason, and the one that would be more at the forefront today, particularly given, at least in the US, the precipitous drop or at least the projected drop in milk product or cost again, or value again, is the value and the cost of that nutrients in the diet, okay? So if we look at these summaries that are done quarterly by the group at Ohio State, Norman St. Pierre developed a program that they use to take the various ingredients that are available in the Ohio Valley and off into the Northeast. And if you use a large matrix of those ingredients, and the prices that they're currently selling at, and of course the nutrient content of each ingredient, statistically you can work out what the value is for the various nutrients that we're feeding to the dairy cows, okay? So of course we're feeding cows ingredients, but their requirements are not for the ingredients, they're for the nutrients, right? So they need a certain amount of energy, a certain amount of metabolizable protein, effective NDF, and of course they need vitamins and minerals. And so what they can do is work out, at least for these three nutrients, plus when we purchase ingredients, you know, particularly with the byproducts, we get a bunch of non-effective NDF that's sort of short in length and not of value from an NDF standpoint, but it is of value in terms of the energy value from it. So if you look at the costs that they've derived on average over the last 5 years, the net energy of lactation is worth about 8 cents per megacal, okay? And so if we take a cow that's making 80 pounds of milk with 3% protein and 3% fat, her requirement would be 35.4 megacals. So if I multiply the 8 cents per megacal times the 35.4 megacals, the cost for feeding that cow energy each day is roughly $2.83. If we look at metabolizable protein, then its historic value over the last 5 years has been 43 cents a pound. And this cow that we're talking about would require 5.44 pounds of metabolizable protein. And so again, multiplying, I end up with $2.34 per pound, or I'm sorry, $2.34 per cow per day to feed that cow the protein that she needs. Going through the same exercise for effective NDF, which is basically long fiber and forages and so forth, we add another $1.46 to the diet costs. And then we can subtract off about 15 cents for the fact that we're getting a lot of this NDF for free. It's all short in length and therefore it isn't an effective fiber source for rumen function. And of course, it tends to have a negative value because if you take a byproduct, the more NDF it has in it, the less energy it has, right? So it's sort of an offset for our energy derivation. So we can subtract off about 15 cents. And so we end up with about $6.48 per day to feed the cow energy, protein, and fiber. Of course, we have to add on a bit more for some vitamins and minerals. But you can see that the protein cost, you know, roughly represents about a third of the cost of feeding the cow a day. So if we're wasting, you know, 75% of that, well, then a lot of that $2.34 we're spending is actually being wasted. We just need to figure out how to feed the cow more efficiently, and we can reduce the cost and, you know, the required supply, and therefore the cost of providing that to the cow. Now these are estimates based off of sort of a survey of the cost of ingredients, you know, at a particular time. You can also arrive at these by using what's typically been called least cost formulation or diet optimization. And this is out of date. This was done by a student in our group in 2013. So the value of the ingredients at that time, of course, are not reflective of today. But I think the point that you can see from this graph is still valid today, in that if we go for high protein diets, the cost is going to be higher because we're putting more protein in that diet. And as we reduce the requirement for protein in the diet, and these are just artificial requirements for crude protein, each of these diets that I balanced are all sufficient for MP, sufficient for energy, and sufficient for the vitamins and minerals and fiber for this cow producing roughly 80 pounds of milk at 3% protein and 3.6% fat. But I forced the crude protein up, right? It was cheaper to actually let it solve for lower crude protein levels. So it's much cheaper to feed the cow to meet her requirements at 15.5% crude protein than at 18% crude protein by, you know, roughly or a little over 20 cents a cow a day. Now, given the model that we're using, the NRC 2001, it's not cheaper to try to feed that cow below 15.5% crude protein, because you start kicking out ingredients like wheat midds and distillers grains and things like that that can provide energy, but they also provide protein, and we're therefore not allowing space for that protein to come into the ration. And so you can see that at the very lowest, at 15.25% that I could get to solve with that model and those ingredients, the price went back up to nearly $7 a day. And actually that ration was not a feedable ration. It was too high in fat. It was loaded up with salt. And so it was doing all sorts of strange things just trying to get it to solve. So the cost or the value that's there to capture is somewhat difficult to derive in terms of figuring out what it is for each farm, unless you go through an exercise with the optimizer to determine it for your farm for the prices today. But in general, definitely there's cost savings to be had if we can reduce protein in the diet. And we do gain, of course, efficiency as we do that as well. And as a reference point, in terms of trying to get an idea of just how much progress we might be able to make, if we look at what pigs do in terms, or what they're able to do with their best knowledge, where they're feeding a lot of pure amino acids, their retained nitrogen to absorb nitrogen efficiency can be as high as 80%. Now, they don't operate nearly that high in the industry because that actually costs more than operating at a lower efficiency, but that's the range of their knowledge base. They can operate anywhere between, probably 20% efficiency and 80% efficiency, given their knowledge. For comparison, because a cow, of course, has a rumen that they have to maintain that may either add or subtract from our efficiency. If we look at milk nitrogen divided by absorbed nitrogen, so it's comparable to what we're looking at for a pig, we operate at about 35% efficiency. So we have a lot of room for potential improvement here to get this cow to work better if we understand how to feed them better. And so let's look at it one more way, because requirements, of course, are important, and requirements are what's driving those optimization runs that I provided before. These are some data that Helene Lapierre summarized, seems like just a couple years ago, but time really flies by. And of course, we have probably 3 times as many data points that we've been using over the last 4 or 5 years. I need to update this slide, but it makes the point, and perhaps having more points on it will just clutter it up more. But the point to make here is that essentially what we use for our ration balancing software and our knowledge base is what's reflected by the line through the middle of these points. So the points reflect small groups of cows that were fed individual diets on a variety of research trials conducted over a long period of time. And the line going through the middle would hopefully represent our model. Now, actually, it doesn't. The model doesn't go through the middle of the data like this line does, but it should if we have it correctly set up, all right? So let's assume that we can get a model that goes through the middle of the line. If we want 1,000 grams of milk protein a day, then we just extrapolate over to the line and drop another line down to get an estimate of how much metabolizable proteins we need to supply to that cow to be able to achieve that. And so you can see here that we need 2,650 grams. And so if you plug this, into this kind of a cow into the NRC 2001 model, that's roughly about what it's going to give you for a required MP supply. But the point of interest, I guess, from our standpoint and from society in general is, of course, there's a whole bunch of animals or groups of animals that performed above the line, okay? And those are of interest because all those dots above the line actually got more milk protein than predicted by the model, given a supply of metabolizable protein. So they were more efficient, those groups of animals were, than the average that we assume in our requirement model. Of course, there's animals that were less efficient as well, but we're not as interested in those because they obviously are not going to be beneficial for making our system run more efficiently and therefore more economically. So if we focus on those and we sort of estimate the outer edge here, saying, well, there's a bunch of animal groups that actually performed, quite a bit better than the model. So if we sort of draw in a line out on the edge and say, what would be the case, in terms of our feeding requirement if we were using that knowledge base, right? If we had that knowledge base to reliably feed out there. And so you can see that that new dashed red line now intersects my desired 1,000 grams of milk protein at approximately 2,000 grams of MP. So it's a 650 gram differential, right? Now, living in the US, we still, have this sort of archaic and maybe sort of quaint system of measuring things, okay? And so we have to, as scientists, we tend to work in a more reasonable world, but we have to then convert it back to the US units, all right? So let's take the 650 grams of MP savings that we could get if we were able to feed cows at that higher efficiency, convert it to pounds so that we can multiply by in this case, I used 44 cents, which was the last quarterly summary of, 6 months or so ago from Ohio State. So just 1 cent more than the average over 5 years. We see that equates to 63 cents a cow a day. So if those relationships hold, as we move from 2650 to 2000 and increase efficiency of our diet, we potentially could save 63 cents a cow a day. Well, that's a massive savings, right? I mean, that is the difference, that is all the difference in profitability, and certainly, would cover probably most of the losses that have occurred over the last 4 years if all herds were operating at 63 cents a cow a day, greater profit. And so if we look down at the bottom too and look at the efficiency for MPUs, okay, so it's basically 1,000 grams of net protein deposited in milk divided by on one case 2,650 grams of MP, that's a 38% efficiency. And if we take the 1,000 divided by 2,000, probably any of us can do that in our head, I certainly can, that's 50% efficiency. So we're still not at 80% efficiency like swine, but it's a pretty significant step in the right direction. So the question is, how do we achieve that? Can we reliably do that on farm every day? And, can we capture a bunch of those savings for the producer? And of course, as business people providing services, if we can make savings and make things cheaper and more economical, there's an opportunity to capture some of those savings in terms of profits as well. So what's holding us up, or how do we get there? Well, you as end users basically mostly see your computer, right, in terms of doing rations. Of course, you're looking at the cows and you're trying to gauge how well they're doing, and you probably have developed thumb rules and sort of standards that you use based on what you see in the cows to help you make adjustments to the computer software that you're using. But mostly when you're sitting down to work with that software, you see two things. You see the feed library, which you're using to select feeds, and then you manipulate the feeds that you selected to reflect the nutrients that are in those feeds, and the reports, okay? And you're monitoring the reports to see whether or not the supply of nutrients that you've provided actually is meeting the requirements, which are going to be listed for you on the reports. And again, back to your thumb rules, you've probably discovered that sometimes you can get by with less than what's specified for a requirement. And in fact, you probably have found that with MP in general, that lots of times you can probably get by with less than is required. And RDP is the same thing. You definitely can get by with less than is specified as required on those reports. So what's making that requirement, okay? And what's relating that requirement to the feed library and the supply of nutrients? Well, of course, it's the part that you probably don't, see very much of, or don't see much of, and that's the cow model that's in there, right? It is the model or the set of equations that take the feed ingredient inputs that you've provided and calculate a nutrient supply for each of the major nutrients based on those inputs. And then it also calculates based on your desired level of production what the requirements would be for each of those nutrients, and provides a balance which it then reports out to you. And it's those relationships that you're seeing. And it's that cow in the middle that provides that line through the middle of the data. And it's that cow, or that representation of the cow, that we would like to manipulate a little bit to allow it to reflect the ability and the potential to provide diets at higher efficiencies and at lower cost, okay? And the other part that you probably don't interact very much with, or maybe never, is the optimizer, okay? And most software today has an optimizer in it, because the relationship between that feed library and the supply of nutrients and the requirement for nutrients has become very complicated. And so undoubtedly you are very good at solving rations to generate a diet that will achieve the farm's goals, and it's going to be a safe diet to feed, and you do that day in and day out. But I think the part that maybe is getting missed, and I'm only going to touch on this briefly again, is the fact that because there's so many things you're trying to balance, yes, you're doing a good job of providing a ration that will work, but I think often, or probably maybe almost all the time, there's probably a ration that would also work that would be cheaper and would generate more income for your customer. And so I think that's what should cause you hopefully to invest some time again to, relearn how to optimize, or if you knew it before, or if you didn't, then learn how to optimize rations. It can be frustrating at the beginning, but with some practice and some investment of time, it actually can become quite easy for you to do. Yes, it takes a little more time, but if you can save 10 or 15 cents a cow a day, isn't that worth your time? All right, so let's go back to that model, because everything sort of revolves around that model. And of course, we do have to have accurate and precise inputs to the model. So getting a good feed sample and getting it analyzed at a reputable lab is of course very important. It doesn't matter how good the model is if we have bad inputs. So that part of the job is on your side of the fence. Getting the model to work better is more on my side of the fence, okay? And so just briefly touching on the concepts of accuracy and precision as they relate to models, we can think of it like a target, in target practice. So if we have a target and we're shooting arrows at the target, or darts if you prefer, then of course we would, if we're being accurate, we would like to have those arrows or darts being received by the target, around the center of the target. And the more precisely, the higher precision, more precision that we have, the closer all of the arrows that we throw or shoot will be to the center of the target. So accuracy refers to the fact that our collection of darts is around the center, okay? It's centered around the very middle of the target. Precision refers to how closely those are grouped. So in this particular example, we're both accurate and precise. All the darts, are close to the center, and they're evenly distributed around the center. So when you look at some of our statistical summaries that we'll use, and I'll show you later, if you have a case like this, then that when you take the distance from the center to each dart or arrow, and you sum up those distances, those deviations, you square them first and sum them, you end up, if everything's close to the center, you end up with a low residual mean squared error, okay, which is abbreviated as RMSE. And another representation of how well the model works is the concordance correlation coefficient, which can range between -1 and 1. So a very good model would have a value of 1. It could also be quite valuable and very good if it had a value of -1, but that would mean everything it told you to do, you'd have to do exactly the opposite, okay? It's basically moving in exactly the wrong direction. So we're trying to get CCC close to 1. We're trying to get RMSE close to 0, right? If it's 0, that means all of the darts or arrows are in the very center of the target. And if that's the case, we would have no sort of accuracy problems. In other words, the darts wouldn't be off one side or the other. And we'd have, when we start moving the target from low production to high production, we would have no slope. They would always be around the middle and evenly distributed around the middle. And that kind of a model is extremely useful because you can rely on it giving you repeatable answers every day. If we contrast that then with this kind of a model, it's both inaccurate and imprecise. The arrows are not distributed around the center of the target. They're way off of the center, and they're not clustered tightly, okay? So they're off the center, so we have inaccuracy, and they aren't clustered tightly. They're spread out all over the place, so we have imprecision. And so basically any predictions by this model are always off, and they're often in a relatively unpredictable manner. That will generate a lot of distance between, so if I take the distance between the center of the target and each arrow and square that and then sum all of those up, I'll get really high root mean squared errors. And the concordance correlation will be very close to 0, or it may be 0, right? And so essentially this model is not useful. It has high mean bias, it has high slope bias. You might be able to figure out how to interpret that over time, but it would take you a lot of time to sort of mentally calibrate that so that you could sort of equate, when it tells me I should do this, I need to add 10 and subtract or multiply by 1/2 and add, 1/3, and then I can get an answer close to reality. And in fact, portions of this are exactly what is the case in the NRC from 2001. So if we look at some of their data that they provided and rescale it to an appropriate scale, this is the observed minus predicted milk production in kilograms per day. And so if we take a prediction by the model and we subtract it from the observed that the cows actually did, if the model prediction was perfect, when we subtract, we should end up with a 0. So these points should all be lined up along the 0 line as the model predicts from low production to high production. And of course, they're not. They have a slope to them. And so the model is actually in the low end here, up until about maybe 30 kilograms of milk per day. It is sort of clustered around 0. You can see, though, it's moving away from that 0 line over that distance. And it becomes quite obvious above 30 kilograms of milk that the model has a problem, okay? By the time we get up here in the 45 kilogram range, it's providing answers on average that are almost 7.5 kilograms off of what's really happening with the cows. And we do have some precision issues. It's maybe not terribly bad, but you can see that the points sort of scatter about this line by about 5 to 7 kilos. Okay, so when it tells you that you've done a diet for 40 kilos of production, well, first off, that's off by about 4 kilos on average, and that production average could range by plus or minus 5 kilograms. So if we look down at the statistical summary, the RMSE in terms of a percent of the mean is 23%. So when I go back to my 40 kilograms of milk, I'm providing that prediction for the farm with 23% variance or 23% error. It's going to be somewhere between 40 plus 23% and 40 minus 23%. Okay, so we have a mean bias of 5.3 kilograms or percent. Okay, I'm sorry. We have a slope bias, and that slope is almost 1/3. Okay, so for every kilogram of additional milk the model predicts, it's about 7/10 too high. Okay, so when you predict an additional kilogram of milk, the cows are only going to give you about 0.7 kilograms of milk. So those problems, had to be fixed. Okay, and I can, happily report that, at least from an NRC committee standpoint, that we have addressed essentially all of those problems. And it required, a concerted effort on all committee members, and so there's a broad range of things that were done to improve that model and that system, starting with an updated feed library. So all the nutrients are updated based off of commercial lab values. So now we have thousands of samples of each feed that are providing an estimate for what the average should be for soybean meal, for example, plus it's giving you a variance on that. And the nutrients, in addition to those commercial lab provided nutrients, we also updated all of the KDs for proteins and all of the amino acid composition values. Having done that, then we started testing the model and identified, as have others, that the RUP estimates were biased. And essentially, trying to cut the story short on this, both the estimates of the rate of passage from the rumen and the rate of degradation from those in situ observations are off. KD is too low by in situ, okay? That bag is apparently impeding migration of the microbes and the enzymes into the bag, and it's providing too low of digestion rate estimates, and KP is too high. So those, like the rate of passage as estimated by those heavy metal markers, that were primarily used by the group at Cornell to derive those equations, result in too high of estimates. We did not find, a universal solution to this problem. Okay, we basically ended up with a Band-Aid approach. If we throw out the whole system, then we lose our ability to get sort of rapid turnaround of estimates for novel new ingredients. If we keep the system, we need to at least center it, okay? And so basically we kept the KDs, even though we know they're wrong, and we refit KP to remove the bias, okay? And that essentially removed the problem from the system, but it's basically removing it by taking two wrong numbers and multiplying them together to get a roughly correct answer, okay? So it's a Band-Aid fix, it's not an absolute long-term fix. More work is needed on that. We did, in addition to fixing RUP estimates, we updated all of the RUP digestibility estimates. A new microbial crude protein prediction equation was developed by Luis Moraes at Ohio State based on our new RDP estimates and also new estimates of ruminally degradable carbohydrate. And that new equation now is an integration. It integrates both the energy and the protein supplies to provide a much more precise and accurate prediction of microbial flows. We updated amino acids throughout, okay, all the way from the feed library to milk protein. Every part of that system was basically touched and corrected. And in particular, we needed to correct for the amino acid hydration, which was ignored, and it's a 15% error throughout. And also we corrected, and Hélène Lapierre did a lot of this work for recovery from acid hydrolysis. Not all those amino acids, when you hydrolyze those feed proteins and milk protein on the other end, or body protein, are recoverable from those analyses. And so there's a recovery issue where the recoveries are always less than 100% that was ignored in the past. So those two problems were both addressed throughout again. And we updated the microbial and endogenous amino acid composition. And the one thing that was retained from the old system was the assumption that the digestibility of the individual amino acids that are present in RUP, we retained the assumption that those digestibilities were equal to the digestibility of the RUP. And I'll show you some data later that that's wrong, but there's not enough data to actually move away from that assumption. So additional data are required there. And there's a brand new milk protein equation, which uses 6 essential amino acids, digestible energy, and digestible MDF as drivers, primary drivers. And so it's moved away from, there is no MP term at all in it, okay? So we're moving to driving things off of essential amino acids and energy, rather than driving it off of energy and metabolizable protein. So much more in tune with monogastric nutrition efforts. There's also a new milk fat equation that's driven off of dry matter intake and fatty acid intake, and then a couple of specific fatty acids. And I won't touch any further on that. So a lot of work went in. And so I just briefly want to show that, yes, we sort of applied a Band-Aid to the RUP stuff. It's still, a bit of an issue. And part of the issue is that you can see from this plots is that measurement is really hard to make, okay? You're making a total nitrogen flow measurement based on a lot of marker work. Then you have to measure microbial protein flows. and then by difference you get RUP. So all of the errors and everything accumulate in this measurement. So no matter what we do, we're probably never going to have a perfectly clear picture of this entity given the current measurement methods, okay? Unless we come up with a more precise way of measuring this, it's always going to be problematic. But you can see from the dashed dotted line, which is the model, it now essentially fairly closely aligns with the solid line, which is the line of unity. And therefore it's going through the middle of the data and basically tracking with the data. So when we predict more RUP, we are in general getting more RUP out of the system, right? And so we still have a 40% error in the system, okay? But most of that is probably measurement error, probably 25, percentage units out of the 40 percentage units are measurement error. We have no mean bias. We have a very minor proportion that's slope bias. So we feel like we've resolved the issues here and that this now provides a more reasonable estimate for RUP. I'm not going to show you the microbial equations. They actually have like a 20% error, so they're actually better because that's a direct measurement. And that paper will come out, hopefully in the next year. But of course, when you put the two together, we're interested in the amino acid flows, right? Because that's what our end product's going to be. And they fall in between, as you might expect, right? They're the amino acid flowing out of the rumen as a function of the microbial protein and the RUP primarily, and a little bit dependent on the endogenous flows. So as you might guess, if you have a 40% error in RUP and we have about a 18 to 20% error in microbial, we get just about in the middle of that for the amino acids. But the primary message I want to deliver here is that they're centered in the data now, okay? They were not before. They track with the data, so we get concordance correlation coefficients in the 0.4 to 0.5 range, which says we're capturing about 50% of the variance that's there. So essentially, we feel like we can trust these, even though there's still a bunch of unexplained variation that we feel is mostly associated with just making the measurements. Now, those are historical values. And so what we need to think about from a field standpoint is when you choose a particular ingredient, in this case, blood meal from the library, and you use those values out of the library, they're obviously not going to reflect every blood meal that you would see on farm. And ideally, you'd have some kind of a more real-time measurement that you could make. And so for those measurements, we do rely on these in vitro approaches. And so I just want to touch on a couple slides here relative to the accuracy and precision of those. And this is work that Carrie Estes did for her master's, and the manuscript is just about done. She's recently had a child, so that's sort of put a little damper on her productivity here recently, at least productivity from the research side. I think productivity from her mothering side has been quite high. But at any rate, she did this trial where we looked at blood meal, and I'll show you the feather meal in just a moment. We used an isotope dilution approach to assess the true availability of the amino acids from those two ingredients in cows. And then she summed up the average. She averaged the amino acid availabilities to get an estimate for RUP availability. And she also did some in situ measurements of RUP availability or RUP estimates from in situ analysis. And then she sent off 10 subsamples of each to these three different, it was actually two different labs, one lab doing two different assays and the other doing one assay. And 10 samples of each, so they're just subsamples, they're all the same thing, to assess how well those labs actually performed the in vitro estimates. And so you can see that the three different approaches, generated about the same RUP estimates for blood meal. Their estimates were higher than what we measured by duplicated in vitro incubation or in situ incubations in cows. So the lab-based RUP estimates may be overestimating RUP a little bit in terms of blood meal. But more importantly is what was the digestible RUP? And this is accounting for the digestibility of the RUP and also the RUP amount. So it's accounting for both the left-hand measurements as well as the digestibility estimates. And these were done by the Ross method was used by both labs. And then we did the older three-step method in one of the labs, okay? So you can see that these points, the red bar again represents the isotope-based estimate, which is fairly precise and well carried out. And we also verified that we got the correct answer with casein infusions and some pure amino acids, right? So this is our gold standard, essentially, if you want to call it that. And if you look at the two Ross methods, the first two bars, the gray bar and the black bar, you got quite different answers for the same ingredient that was submitted to the two different labs. They have pretty good precision on their measurement, but their accuracy varies. And the first lab, actually, the lab 1, came really close to what the in vivo measurement was, whereas lab 2 overestimated the digestible RUP content of that ingredient by a considerable amount, and as did the older 3-step method, okay? So if you summarize just briefly, lab 1 got about the right answer and lab 2 got too high of an answer, okay? If we flip to the feather meal and add in then some library values, you can see that the different assessments, okay, and so I've switched things up a little bit. The red bar is still the in vivo estimate from Estes. I just switched the order a little bit. So the red bar is first, then lab 1 Ross, lab 2 Ross, and the modified 3-step from one of those two labs is the 4th bar. And then the 5th bar is the Cornell 6.5 library, the 6th bar is the NRC 2001, and then the last bar is the NRC, I call it 2020, but it's not going to be out till next year, so I was overly optimistic on our time frame. But at any rate, you can see that the 3 labs, or the two labs and the in vivo estimate that we conducted were fairly similar in RUP. They were all greater than what is in the CNCPS library and what was in the NRC 2001 library, but they're not too far above the newer NRC library. If we go to the digestible RUP then, which is going to rely on those RUP numbers as well, the in vivo provided an estimate of about 65% for this feather meal source, which is considerably greater than the 2 Ross techniques conducted by the 2 different labs, and a little bit less than the old modified 3-step method conducted by one of those labs. The CNCPS model essentially gets roughly the correct answer, but of course it was way off on RUP, so it's getting the correct answer by multiplying 2 incorrect answers together. The NRC is also getting close, well, it's underestimating some, and the new NRC overestimates slightly. So I think the bottom line is that when we look at this ingredient, both labs way underestimated. So I don't think you can rely very much at all on these in vitro techniques to give you real-time estimates of the various ingredients. Okay, now we've only estimated 2 ingredients here, but if you have this much trouble on 2 ingredients, then certainly there's going to be a lot of variation among the other ingredients. So coming back to that amino acid digestibility and maybe increasing my pace a little bit here, the bottom line here is when we look across a variety of ingredients that we've done in a couple different studies, with the last 2 being the Estes data for feather meal and blood meal, you can see there's a lot of variation in the availability of individual amino acids. So for example, the leucine availability from corn silage, now it's not a high source of that, is fairly low. And if you look then at distiller's grain, it's high, right, relative to the average. If you take the average of each of these ingredients, they sort of reflect what the RUP digestibility is, and the deviations away from that average then would reflect the variance among the amino acids. So this assumption that all of the amino acids are digested to the same extent as the overall protein is clearly incorrect, and we need to work on that over the next few years to try to provide more data to be able to inform the next version of the model so that we can account for some of these differences. So where are we at? That's all supply side. Where are we at on the requirements? Well, if we look back to poultry, for example, they probably have the equivalent of a supercomputer and a laser that they're using to sort of design their diets. And they can, as I mentioned before, they can move up and down the crude protein matrix and decide whether they want to feed higher crude protein with less purified amino acids, or low crude protein with a lot more purified amino acids. And essentially, they're making those decisions based on profit, right, or income over feed costs. And so they can make high efficient diets if they want to. It's just boils down to an economic decision. If we compare that to, so when they basically design a diet, they have pretty high probability of sort of hitting their target, okay? If we compare that to the ruminant side, or dairy in particular, we do have some knowledge of methionine and lysine that have guided us over the last 10 to 15 years. Those analyses were, highly massaged, and so if you pay attention to the x-axis, the data that they used for this lysine, digestible lysine evaluation, only came from studies where the methionine supply was greater than 1.95% of MP. So they highly selected the data that they used for these, and we really only have a couple of points out here that are actually driving it. If we took away these 2 points, particularly at the end, then your linear line would just keep extending forever, and there would be no break point at 6.9 or 7%, okay, that we would be using as our target. So honestly, in my opinion, I mean, this is a bit like, instead of a supercomputer and a laser, we've got a sextant and a spyglass, and we're, sort of on our sailing ship, wandering around in a cloud bank, trying to find a rowboat that we can hit with our cannon, okay? And so we are plunking balls around the target based on this, and you've maybe learned, some sort of lessons in terms of failures that have allowed you to get better at plunking your cannonballs. But I still don't think it's a very precise system. In fact, I know it's not, and I'm going to show you that here quickly. So if we look at the newer updated data with a lot more points and now lines drawn within study to show the direction of each study, and we start with the NE allowable milk protein, okay, and so these are not directly predicted by the NRC from 2001, but they're using the concepts. You see that the milk protein allowable production based on energy, roughly is centered around the line of unity, but of course it has a skew, right? And that's more evident when you look at the residuals where we're subtracting observed from predicted, right, or predicted from observed. It basically is under predicting performance when predictions are for low milk protein, and over predicting when the predictions are for high. And it's the same skew and the same bias when you look at MP allowable milk protein production. And if we put the two together and use the concept of a first limiting nutrient, it helps with the skew maybe a little bit, and it maybe contracts the data a little bit, but it doesn't fix it, right? The skew is still there, and we still have a lot of variance that we're not explaining. And also, if you pay attention, we're starting to pull the data off of the center line, okay? So we're no longer centered in the data. And if we use that concept and replace MP with all of the individual essential amino acids, it becomes even more apparent. We do not fix our skew, right? We have a bad slope problem through here. We're over predicting our responses considerably, and we've pulled all of the data off the center line now. We're constantly under predicting performance, which would cause us to add more amino acids than what are required. So there's conceptual problems in that model that are leading us down, the wrong path, right? And that the primary one there's two problems to it. One is just the efficiency that we're assuming within the model, and the second one is the conceptual framework where we consider a single nutrient to be limiting at a time. Okay, and so I'll just briefly go through these. These are in vitro data using tissue slices from lactating cows, and so the media was manipulated to provide differing amounts of isoleucine, leucine, methionine, and threonine. And it was a composite design where we did all four of them together at 5 different levels. So there's 5 dimensions to the data, so I can't show that directly. I can just parse out 2 different dimensions at a time here. So if you look at the left-hand edge of the left plot, as we add more leucine to the media, and the y-axis on both of these is the casein fractional synthesis rate. So it's a relative measure, but it is of casein directly. You can see that as we add more leucine, we get increasing amounts of casein. And the red arrows on each of these are the mean concentrations observed in high-producing cows in the field by Swain poll, okay? And so we're operating around this arrow in both directions, and you can see that the cells are responsive to concentrations in that area. And the point that I need to make here is that this front edge is with a constant supply of isoleucine at a very low level. So with very little isoleucine in the media, we can get increasing amounts of casein by adding leucine. If we hold leucine very low and we go to the right, to the lower edge then, and we follow the isoleucine response, we get a really long response above the median for in vivo in terms of casein to the isoleucine. So either one of these can provide an independent response. There's no first limiting amino acid here. And if you move over to the methionine threonine one, it's exactly the same. So if you try to put it together then, and thinking about the fact that we're operating around those red arrows, and I lay a sort of a halo around each one here to demonstrate a specific level of casein synthesis, a relative level of 2.75% per hour, there's an infinite combination of threonine, methionine, isoleucine, and leucine that falls on that line. And that's essentially what you're trying to do in a ration balancing standpoint. You're trying to define, a particular level of input that will yield the production that you want. And so if you start then parsing it out and saying, well, I'm going to decide which one of these first limiting, and I'm only going to add that, you're already on the wrong path. They're all four potentially limiting on any diet if they're operating around these mean concentrations in blood, okay? So if we go then to in vivo and we tried a couple cow experiments that actually numerically supported what I just showed you, but weren't significant. And so in the meantime, I had a student who I was through a collaboration in China do it in lactating mice. So she did a dose response trial to crude protein to look at litter weight gain on lactating from lactating dams when they were fed. The dams were fed dietary protein from 24% down to 6%. And it was a nice dose response curve with a maximum pup weight gain at 20%, 21% crude protein. And by the time you got to 9% crude protein, all the dam ate all the pups, and so you lost your measurement. So we came back and ran the second study with a positive control of 21% crude protein as a representation of maximal pup growth, and then a deficient diet of 15% crude protein. And you can see we replicated our previous results where we got a 20-gram reduction in litter weight gain, which was highly significant. And then to that 15% protein diet, we added individually isoleucine and got a response. Or instead of isoleucine, we added leucine and got a response. Or instead of either of those, we added methionine and got a response. The only thing we didn't get a response to was threonine. So there is no single limiting amino acid on this particular diet. There is limitations of isoleucine, leucine, and methionine, and they all had about equal limitations, and they all provided about equal responses. So the choice of which one you would supplement to the diet, if you wanted to get a little more milk out of these, or pup gain, would depend on the cost of the amino acid and the value of the pup gain. And then finally, Peter, a year or a year and a half ago, and this is published now, I think it's out at least in electronic form, was able to demonstrate this in cows through an infusion study. So we'll only focus on the left-hand plot, which is the milk protein. We had a control diet, and these cows, I'll point out on the right plot, were producing over 100 pounds of milk in metabolism stalls. The control diet was 15% crude protein. The cows produced 1,475 grams of milk protein on that diet. When he infused methionine, lysine, and histidine to try to test whether there is a deficiency, there was. He got a significant response to that of about 75 grams of milk protein. If he infused isoleucine and leucine instead of the methionine, lysine, and histidine, he got a little less milk protein, but it was still a significant response. And if he infused the 5 together, he got the 2 responses from the 2 individuals essentially added together. Okay, so there was, from a stat standpoint, we had a significant response to the first group, a significant response to the second group, and no interaction. In other words, this response over the control is just the additive responses of those 2 individually. So again, no single limiting amino acid, just responses to those that are deficient in the diet. So if you take that approach then and go back to the literature and solve for an additive equation, the terms that end up being significant in terms of explaining milk protein output are the absorbed supplies of histidine, isoleucine, leucine, lysine, methionine, threonine. Of course, energy. There's a little drag from NDF because the energy supplied by NDF is a little less effective in driving milk protein than from starch and fat. And of course, big cows have a higher requirement than little cows. The responses then are, you get 2.44 grams of milk protein per gram of absorbed histidine, 1 gram per gram of absorbed isoleucine, 1 gram per gram of absorbed leucine, 1 gram per gram for lysine, roughly 2 grams per gram for methionine, and 2 grams per gram for threonine. And you get a whole bunch of milk protein out of providing energy. Okay? So we can't leave energy out, or we can't leave the amino acids out. They all add up to provide the observed level of milk protein. So when we look at the stats on that, we've got an RMSE of 13.7%, so roughly half of what we had before. We have no mean bias, we have no slope bias. We have a CCC of 0.8 versus like 0.6 before, okay? You can see from the plots that the data now all align, the predictions all align along the line of unity. There's no slope bias that we have, and basically we can predict from high to low without any deviations. So it's a much better model in terms of providing estimates of what you should do. So just to summarize quickly here, because I'm running too long, does this make any difference? You know, can we use this? Well, if you take a 16.5% protein diet and you drop it to 14.5%, you're going to lose some essential amino acids and you'll lose some milk protein if you don't do anything special. And that's because you have reduced supplies of these essential amino acids. You'll lose based on current prices for milk protein. Based on the Ohio State estimates, that diet will cost about 27 cents a cow a day less, okay? And you'll lose about a dime, well, about 8 cents worth of milk protein value, okay? So it still nets you 20 cents a cow a day. So even though you've lost production, it in theory would be a cheaper diet. If you go another increment, these numbers probably don't hold together because, for one, the value of the MP is probably not going to extend down that far. Of course, you're going to lose more milk protein. But if it did extend and if everything held, then there's probably even more value to be had. But I question really whether that's possible. But you could take that low one and you could fix all the all the amino acid problems by adding rumor-protected amino acids and actually end up with more milk protein. I don't know what the cost would be because I don't know what the MP savings is, and I don't know what the cost of the essential amino acids would be. But if we could do it for this, or even if we can only do it for half of this, there's probably 30 to 40 cents a cow a day on the table there that we have to work with in terms of profit. So there's certainly economic reasons to do this, right? So if I just sum up then, a lot of work was done on the library and the model. There's new concepts that you need to become familiar with in terms of balancing for amino acids and what's driving the milk protein and the milk yield output. There's no such thing as a single limiting amino acid or a single limiting nutrient, okay? Energy supply and the amino acids interact additively to provide the output that you observe. And the milk protein equations are in a trial version of NDS. AMTS is waiting on me to give them the equations. The new NRC will be out next year. And so the one point I'll then close with is that, given all of this complexity now that I just sort of summarized for you on the protein side, and add that to the complexity that we already had on the energy side, do you really think you can effectively sort of plug and chug to get the best solutions for your customers? I'm not doubting that you're getting good rations and that the cows are reducing on them, I'm only questioning whether you're doing it at the most value. You're trying to balance eventually here for starch, NDF, RDP, fat, 8 essential amino acids, at least a couple of fatty acids, 38 minerals and vitamins. You're considering the cost of the ingredients, and you're considering the cost of the milk components. How much money are you leaving on the table when you're doing that by hand? You really need to check the box on the optimized side and retool to acquire that skill and make use of it. I think you'll find you're going to save customers quite a bit of money. So with that, I'll stop, and I'll be happy to entertain questions. Again, I apologize for running over. I tend to talk longer on each slide than I should.
Oh, we do have one question already. What is the ratio between lysine and methionine, and what is dose dry matter basis or TMR basis?
It can be a huge range. Okay, there is no set ratio that's optimal.
Anyone else have any questions for Dr. Hanigan? And if you do have any questions or anything of that nature, feel free to reach out to Mark there. His email there's in the bottom of the current slide, or feel free to reach out to any of us at Zetagrow, and we'll get your questions answered as best we can. Appreciate everybody's time this morning, and
let me,
great weekend.
Daniel, just let me weigh in a little bit more on that question, then.
Okay.
I mean, obviously, my statement is indicating that you could have a ratio of 10 or of 0.1 and it would be okay. Well, we do know that the animals sense when they have an amino acid imbalance, and they tend to reduce intake when they have that. So it's actually not probably the milk protein equation that's going to drive that answer as much as it would be the intake equations. And we don't have that an amino acid imbalance effect represented in any equations because we don't know what they are in cows. We know what they sort of are in mice and rats through a lot of work over the years, but obviously that doesn't equate to a cow. So from my standpoint, I think the best idea is, to not necessarily have an ideal ratio, but maybe have a ratio in mind, and we actually did, Helen has generated those for a target, but don't treat it as an absolute, okay? You can move well away from that target and still be fine, but the farther away from that target you get, the higher the risk you will have that you might induce a dry matter intake depression. So I don't want to leave, I guess, with the idea that absolutely any ratio will work. It won't. But the ratios that we've been sort of targeting in the past are much too rigid. We need to think about it as much more of a fluid environment that the cow can actually tolerate a lot of deviations.
All right, we've got a couple more questions here for you. Based on the differences in amino acid uptake across feedstuffs, is there something that is biologically determining amino acid absorption in those animals? For example, transporter expression or amino acid utilization by the gut?
Yeah, it's not the amino acid utilization, at least as far as we can tell. I mean, there have only been about I don't know, 5 or 6 studies that have been done on that, so it certainly hasn't been thoroughly investigated. But at least the studies that have been done have all been somewhat consistent that the loss of amino acids during first pass, okay, in terms of being lost during the absorption process are extremely low. Okay, they range from 2 to about 10%, and they don't seem to vary a lot. Actually, what causes us the bigger loss is the recycling, right? So the blood flowing to those tissues carries a bunch of amino acids with it, because once they clear the splanchnic tissues, they get by the liver, then they're distributed to the other tissues. And so in our case with lactating cows, that's the primary tissue that's going to be utilizing those. It only takes up 30 to 50%, right? So the other 50 to 70% is recycled back to the general circulation. And when that heart pumps, about 30 to 40% of the blood actually goes back to those splanchnic tissues. So it's not the first pass that's killing us, it's all the recycling that's killing us, okay? And so certainly there would be some losses there, and we've got another model that we're sort of in the middle of getting published that that accounts for some of those losses on recycling. So I don't think it's first pass per se. It might be second pass when you don't keep the mammary gland working at high efficiency. But it could be the digestibility. I mean, clearly, I think it's probably digestibility, and that has not been explored. There's some intrinsic factors in the feed that would limit that. There may be some enzyme problems that we might be able to manipulate the cow to enhance that. Hardly anybody's looked at that, so I don't know the answer to that completely.
The next question is on the blood meal slide. Would you assume the amino acid digestibility is as variable as the other digestible RUP?
It was not. It was actually on the other slide. It's not as variable in blood meal as it is in some of the other ones. So this, I added the last two groups here, right? So you can, I'm sorry, I guess it is more variable than I was remembering, okay? It's the feather meal that's not very variable, okay? The blood meal, the isoleucine, or I'm sorry, the leucine availability out of that is fairly low, and the methionine availability is quite high. So these, you know, all these ingredients have sort of different patterns, and I don't know that there's any, you know, commonality that we've seen so far. But I do want to point out that we could start to try to adopt some of these, but remember, we derived all of the milk protein response equations assuming a common digestibility of the amino acids. So if I start plugging these variable digestibilities in, or variable availabilities, I don't know whether they're available, you know, if it's a digestion or an absorption thing, or a first use. But if we start plugging these into the existing model that I just showed you, it will cause all sorts of havoc. We have to rederive that requirement equation again once we start putting these in place. So keep in mind there's variation there, and maybe, you know, a little bit of caution and sort of getting real wild with what you're doing. But there's not a lot we can do today to sort of correct that problem. It'll take another effort to correct that.
So in your thoughts, Mark, what will be the next step in improving the model for amino acid supply?
I think that's the next step, is we have to actually build up that database of those amino acids. I mean, that's what the swine and poultry people have done, right? They're balancing off of the ileal digestible amino acids, right? Which is sort of the equivalent of what I was showing you with Carrie's work. So we have to build that up. And the other thing that we need is we need some reliable real-time measurements to reflect the variation among feeds, not just an overall digestibility, but of the individual amino acids. And I don't think we're anywhere near that point either. I mean, it's one thing for me to tell you what the blood meal is, or what the values are for that particular source of blood meal. I don't know what the variation is across blood meals. You know, maybe blood meal is not as variable, and it might work pretty well. I can be quite certain that feather meal is quite variable, and the values I showed you for that feather meal may not apply at all to another feather meal. And of course, many of our other ingredients are also quite variable. So somehow we've got to come up with, you know, faster, cheaper methods that are accurate and precise to derive those amino acid availabilities that we can apply to lots of ingredients so that we can get real-time measures. Those are the two things I see as driving sort of the next step forward.
All right, well, thank you, everybody. Thanks for giving us your time on a Friday morning. I appreciate it, and we look forward to seeing everybody soon. Have a good rest of the day. Thanks, Mark.
All right, thank you very much.